For generations, the sovereignty of nations and the accumulation of massive institutional wealth were determined by the control of physical geography, maritime shipping lanes, oil reserves, and fertile trade corridors. However, as we navigate the complexities of 2026, that historical framework has been permanently superseded by a new, invisible resource: computational capacity, or compute. Compute is the foundational utility of the modern era, dictating everything from algorithmic market dominance to autonomous defense infrastructure. Yet, this digital utility is entirely bound to physical, highly vulnerable hardware networks. The global race to secure these processing assets has triggered a profound industrial restructuring, shifting the focus of sovereign governments and elite investment capital away from speculative software applications and directly into the concrete, high-stakes infrastructure that makes advanced processing possible. The most immediate manifestation of this infrastructure bottleneck is visible within the domestic electrical grid. The sheer volume of data processed by next-generation artificial intelligence arrays has pushed traditional utility systems to their absolute engineering limits. In 2026, a singular, advanced data center complex can consume as much electricity as a mid-sized American city. This unprecedented demand has forced a historic realignment in the energy sector, as major technology conglomerates bypass traditional utility providers to secure their own captive power generation. We are witnessing a massive corporate pivot toward nuclear energy, characterized by the direct acquisition of operational nuclear facilities and the long-term financing of small modular reactors. For the institutional investor, this reality establishes a clear baseline. The future of technological expansion is no longer constrained by software architecture, but by the physical availability of gigawatts and steady-state thermal power. Simultaneously, the inner architecture of the microchip itself is undergoing a forced evolutionary leap to survive this energy strain. Traditional silicon processors, which rely on copper wiring to move information between components, have encountered an insurmountable physical barrier known as thermal resistance. At extreme processing velocities, copper pathways generate immense heat and degrade signal integrity. To circumvent this bottleneck, the semiconductor industry is rapidly transitioning to silicon photonics, an engineering paradigm that replaces copper connections with microscopic lasers. By utilizing photons rather than electrons to transmit data across a chip, processing speeds scale tenfold while power expenditure drops by half. This optical hardware revolution ensures that computational throughput can continue to grow exponentially without melting the physical substrates, creating a highly lucrative market for the specialized manufacturers holding the core optical patents. Yet, even the most advanced internal chip design is useless without secure external transit lines. Over 95% of all transcontinental internet and financial data traffic moves through a fragile web of subsea fiber optic cables resting on the ocean floor. These underwater corridors have become the primary focus of modern geopolitical espionage and naval strategy. Superpowers are currently engaged in a quiet conflict to monitor, protect, or potentially intercept these lines, with intense focus shifting toward new Arctic routes opening through the Northwest Passage. These northern pathways offer significantly reduced latency between global financial capitals while avoiding traditional naval choke points. Concurrently, the raw materials required to manufacture these high-velocity networks, specifically critical trace elements like gallium and germanium, are subject to strict export restrictions and international licensing regimes. The nation that controls the primary refining capacity of these minerals possesses a powerful economic lever, capable of disrupting global radar production, electric vehicle manufacturing, and advanced chip fabrication at will. To insulate their national security from these geopolitical choke points, a massive capital migration is underway to establish domestic sovereign foundries. Hundreds of billions of dollars in federal subsidies and private equity are being deployed within domestic borders to build highly automated fabrication facilities. These megaprojects are massive industrial fortresses, requiring specialized localized infrastructure, dedicated chemical inputs, and closed-loop environmental controls. However, building the physical factories is only half of the strategic equation. The ultimate challenge lies in securing the data these chips process against the next great technological inflection point, the quantum decryption horizon, commonly known as Y2Q. As quantum computing systems approach commercial scalability, their ability to utilize quantum superposition allows them to effortlessly bypass traditional cryptographic standards that protect the entire global financial system. The mathematical foundations of modern banking, corporate logistics, and sovereign state secrets face structural obsolescence. Consequently, the transition to post-quantum cryptography has ceased to be a theoretical discussion and has become an immediate, high-priority mandate for global wealth management. The institutions that successfully transition their networks to quantum-resistant algorithms will secure their survival, while those left on legacy systems will find their digital assets completely exposed. The geopolitics of computing is a stark reminder that in an increasingly digital world, true power remains deeply rooted in the physical security, mineral chains, and structural infrastructure of the physical Earth.